好的，大家如果说准备好的话，可以先扫一下这个 slide。那这一场是由旅行带来的 Developing Serverless Rust App Using AWS SDK Rust。那这一场将会用预录的影片的形式来播放。那在会后，在影片播放完毕之后，会有大概5分钟的时间，然后我们会做这个 Q&A， 那就会有各位在 slide 上面提供的问题。来做一个现场的回答。那个旅行本人会加入 Google Meet， 然后回答一些各位的问题。好，这边有没有还没准备好这个 slide 的？可以举个手让我知道。如果没有的话，我们就开始接下来的 talk。
Hi, thank you for having me here. My name is Xing. I'm a solutions architect in AWS. I mainly work with customers in the Benelux region, focusing on manufacturing. So I have a lot of experience with machine learning, IoT, but also Rust is my personal hobby. I've written 2 books on Rust, and I was quite active in the Rust community. So today I'm going to talk to you about how to develop a serverless Rust application using AWS SDK for Rust. What we're going to cover today is, first, what is serverless? Why do we use Rust for serverless? We're going to look at a simple architecture of a REST API that uses Rust code running on AWS Lambda to fulfill the API. I'm going to show you some of the toolings that we use to be able to compile and deploy this architecture. And we're going to show you a little bit of the code snippets. Finally, as a bonus, I'm going to talk about how AWS works hand in hand with Rust. So first, what is serverless and why do we use Rust for serverless? So imagine you have your own data center, you manage your own servers, then you are responsible for everything that you have, right? The physical buildings, the cooling, the power, the servers themselves, the networking, the hypervisor. You also have to make sure the operating system is up to date, patched. You have to deploy your own programming language runtimes and frameworks. Finally, you need to write your code for sure. If you move that to the cloud and use a virtual machine service, for example, EC2, then some of the responsibilities are shifted to the cloud vendor, right? Like the hypervisor, the hardware, and the data center itself. AWS would handle that. You only need to take care of the operating system, language runtimes, and the application code. Can we push this idea even further and move the line higher up the stack? Yes, we can. So if you use serverless services like AWS Lambda, you only need to provide a piece of code, a function that handles an event. The language runtimes, the operating systems are all handled by AWS. So why do people use serverless? As you can see in the previous slides, there's much less thing you need to worry about. That translates to agility because you can focus on your business logic, you can build software and test it faster. You can move it into production much faster because you don't have to purchase the machines, you don't have to set them up, configure them. You just provide the code and you're ready to go. The performance might also be better because it scales much easier. AWS Lambda has built-in auto-scaling, so it will increase the capacity based on if the traffic goes up, and it will reduce it when the traffic goes down. That also could be a cost benefit because when you're using serverless, you pay in a pay-as-you-go model. So you only pay for what you use. If your Lambda function is sitting idle, you don't pay for it. Whereas in a traditional virtual machine or your own servers, you need to keep them on at all times and you're constantly paying for that cost. So when you're moving to AWS Lambda, you could save some cost. And finally is the security, because you have better isolation between your Lambda functions. More of the management, like operating system patching, language runtime updating, those are handled by AWS as well. So you get better security with much less work. So here are some of the serverless services that we just saw. AWS Lambda. We also have AWS Fargate, which allows you to run containers. There are data stores like S3 bucket for objects. There are databases like Aurora Serverless or DynamoDB. There are also quite a few integration services that let you build event-driven architecture like EventBridge, SQS, SNS. We also have API gateways for you to build REST APIs or WebSocket APIs. We have step functions for orchestrating workflows. So these are all serverless services that you don't need to manage the underlying infrastructure yourself. So why do we use Rust for serverless? You might say, wait a minute, like this is the exact same slide that we saw before, right? Yes, Rust works well for serverless for some of the same reasons. First, you get agility because you get compile time checks, so you have a shorter life cycle. You don't need to deploy your code all the way to the cloud and then realize that you have a runtime error. Those are captured in compile time. Rust is known to be very performant. It can run really fast. And there's also interesting research on the sustainability of programming languages. And Rust actually consumes much less energy for the same performance. So it could also be a sustainability concern. Because the cost is based on usage, right? But if your Rust code runs fast, the duration that you incur costs are much shorter. So you could potentially save some cost by using Rust on AWS Lambda. There is a lot of focus on security, memory safety. There are a lot of encryption crates and security-related crates. So you can write really secure applications using Rust and Lambda together. So that's for the rationale. Now we're going to show you a little architecture that we're going to build today. So this is an architecture of a REST API that is coming from the template that we will see shortly. So you will have a single page application that talks to an API. The API is using API gateway to expose the API to the internet. When it receives a traffic, when it receives a put request, it will trigger a Lambda function. And the Rust code is running inside the Lambda function. It will use the AWS SDK for Rust to connect to and write the data to DynamoDB, which is a NoSQL database. And optionally, you can have your static front end located in an S3 bucket and served through CloudFront CDN. But that is out of scope for today's talk. So how do we deploy that? We're going to see some toolings. AWS provided quite a few of the tools, of frameworks, and CLI tools to deploy those things. The first that we will see is the AWS SDK for Rust. It's in developer preview. It gives you Rust programmatic access to AWS services. We also have the Rust runtime for AWS Lambda. So if you want to run Rust code inside AWS Lambda, you can utilize this Rust runtime. There is also a cargo tool called Cargo Lambda. is a cargo subcommand which you can install. What it does is it handles compilation and packaging of your functions. So it will take a Rust code, compile into format AWS Lambda accepts. And if you're using cross-compilation, then Cargo Lambda uses Zig under the hood. So Zig is another programming language. And we are not using the language itself, but its tool chain is actually a great linker for cross-compilation. So there is a subcommand called cargo zig build, which uses Zig's linker to help you cross-compile Rust code much easier. So if you are using a different architecture for inside your Lambda and your development machine, then Cargo Lambda will invoke zig build for you. Finally, to tie everything together and deploy those services, we have the AWS Serverless Application Model, or AWS SAM for short. This framework provides you with a CLI and also infrastructure as code templates to deploy them without manually clicking through the console. So let's take a look at So because today we're at open source conferences, so these tools are all released under open source license. For example, Apache 2.0, MIT licenses. So let's take a look at the diagram showing you how all these tools tie together. So on the bottom left, you have your code, your Rust code, your template, the YAML, which is the infrastructure as code template for AWS SAM. First thing you do is invoke a makefile provided by the template. This makefile will trigger Cargo Lambda, which builds your Rust code into a binary artifact. Then you will trigger the AWS SAM CLI. This CLI will upload these binary artifacts and the template to an S3 bucket. So the SAM CLI will also trigger a CloudFormation deployment. So the CloudFormation deployment will pick up the template, the YAML from the S3 bucket, and then it will create all the infrastructures that we talked about. We'll create all those individual services, and then the Lambda function will also get the code, actually the binary artifacts, from the S3 bucket. So how do we create these projects? You need to use the SAM CLI. So SAM CLI has a command called SAM init. When you run them, it's going to be an interactive command line tool to help you create your project. It gives you a few templates to choose from. So we can choose AWS Quick Start templates. You have a few examples. We use the Hello World example. And Hello World example actually contains multiple different templates for different languages like Python, Node.js, Java, .NET, Go. So we are going to pick the Rust one, and then it will ask you about a few configurations and project names, and you can just click through them. You will also notice that the Rust template actually has a keyword behind it called provided.al2. This means that we're using the custom runtime. So AWS Lambda provides you a way to deploy your own custom runtimes that is not natively supported. And then the AL2 means that it's running on Amazon Linux 2 distribution. So once your project is ready, you have all the codes. We'll look at the folder structure shortly. But then you can start building and deploying this example. So to build it, you run make build. Under the hood, it will invoke Cargo Lambda build, and then it will put the output binary into target/lambda/ your project. You then run SAM deploy. This triggers the SAM CLI, which will deploy your infrastructure as code inside template.yaml, and then upload the Rust code for your Lambda function and create everything for you. Once it finishes, you can go to the AWS console and you will see a Lambda function with an API gateway trigger. So when you call the API gateway, it will trigger this Lambda function. Okay, so enough for the tooling. We will take a look at some example code. So what you get from the template is this kind of folder structure. On top of it, you have the cargo.toml file because it's a Rust project, right? You have the make file. The make file uses cargo lambda to build your code. If you are doing cross compilation, it will also use cargo zig build. There is a template.yaml file. This is the SAM template, which is an extension of CloudFormation. CloudFormation is the infrastructure as code service for AWS. And by saying it's an extension, that means SAM provides you with some higher level abstractions or shortcuts to help you create serverless applications much faster without writing all the details of the CloudFormation template. Finally, you have the source folder, which contains a main.rs. This is the entry point for your Lambda function code. Of course, there's a README which you can read through. In the cargo.toml file, you will see that we use a few dependencies. So first, it's important to understand how the AWS SDK for Rust are structured. So because AWS has many different services, each one of the service will get their own crate. So they are named AWS SDK and service name. So for example, we are using DynamoDB, so we are going to use AWS SDK DynamoDB. There's also a crate called AWS config. This handles the configuration and getting the credentials and providing the credentials to your SDK services. We'll touch upon that in the code example. You also see that we use a crate called Lambda HTTP. That is the Rust runtime for Lambda. The HTTP means it's specialized for HTTP traffic because you can use a Lambda function for generic, general purpose compute. But in our case, we're building an HTTP REST API, so the HTTP is kind of optimized for the parsing the input and structuring the output. The AWS SDK for Rust use a lot of asynchronous code, so it needs a synchronous runtime. We're using Tokyo for this case. And let's then look at template.yaml, which is the infrastructure as code. This is an extension of CloudFormation, so you will see a similar syntax to CloudFormation. In the beginning, there are some standard declarations, but the important bit is the resourcing part. So first, we see that we create a table with the type AWS Serverless Simple Table. This is one of the abstractions that I talk about. It will create a DynamoDB, but it uses a lot of smart defaults, so you don't have to configure all the required options by yourself. And then we also say it has a primary key, which is ID of a type string. Then we create a function. The type is AWS Serverless function. This is actually AWS Lambda function. You provide a code URI, which is the output path of our Rust code. We choose the architecture, which is x86. And then this function will actually receive events from an API source. The API, when you choose the type API, then SAM will create an API gateway for you under the hood. We also define a path and method like put/ID. So all the paths will be configured in the API gateway. And we don't want to hard code our table names. So we use a DynamoDB, so we use an environment variable to pass the table name to your function, and it's referencing the table that we created in the previous page. A Lambda function by itself also doesn't have permission to write to a DynamoDB, So we have to give them a DynamoDB write policy. Then we can take a look at the main.rs file. So the main.rs file first contains the entry point. It's a sync function, so you use the Tokyo runtime. It calls AWS config load from the environment. This actually loads a lot of the configuration like regions and credentials from the environment. So it knows where to look for your credentials. It could be an IAM role, it could be a configuration file, it could be an environment variable. It has an internal logic that resolves these credentials. Then afterwards, when you are actually making SDK calls to these services, it will use the credentials that the config picks up. We read a table name from the environment variable, and then we create a DynamoDB client. This comes from the AWS SDK DynamoDB crate. Then we trigger lambda HTTP run. This starts the main loop, which whenever it receives a request, it will call the put item function. So the put item function is a simple function that takes the client, the table name, and request. At first, we try to extract information from the request, like getting the pass parameters, getting the body, determine its type, and do some conversions. Then the actual important bits comes from here, when we call client.putItem. This creates a put item request. So on the right-hand side, you will see the HTTP request. This is equivalent to the code on the left. So when you call the code on the left, the SDK will actually format this API request and call the DynamoDB API. So you create a put item request, which is to write data into DynamoDB. You provide it with the table name, and then you use item, which adds a key value pair to the item that is going to be write into the database. Give it an ID, give it a payload, which is the body, and then you go send. This will send a request to AWS SDK. And then in the response, you can, based on how the SDK responds, you can either respond with 200 OK or 500 error. The distance for writing, we can also look at example if you want to list all the data in the table. Then instead of put item, you call scan, and then give it a table name. And because there might be a lot of outputs, you can turn it into a paginator, and then get the items and then send a request. Once you get a request, collect them into an array. But because DynamoDB results has its own format, which is sometimes hard to work with, so you can use a crate called SerDynamo. Allows you to easily convert those DynamoDB results into a normal struct. So you can define a struct like item, which has ID and payload, those are strings, and then use the from items function from SerDynamo to convert them into a vector. Finally, you can use SerDJSON to serialize that to a string for your response. So what you get from the SDK, you get the credential providers, which is the config, which search for the credentials and then use that for your subsequent API calls. It provides you with pagination and also automatic retries. You can do logging with the tracing and log facade. Currently, it only supports Tokyo, but there is a plan for supporting alternative async runtimes. You can look at these public roadmaps in the link I provided here. Here are some resources like the GitHub repo, the list of crates for different services. You have the developer guide, which teaches you how to use the pagination and also retry. There's some example code for different services. And then there's a public roadmap that accepts contribution and discussion from the public. Finally, a little bit of bonus. So AWS and the Rust ecosystem actually are very close together. So AWS is a user for Rust. We build quite a few services using Rust, which I will show you a few examples. AWS is also a contributor to Rust. We are the founding member of the Rust Foundation. We contribute a lot to Rust in Tokyo. And as a cloud provider, we provide you with the tools that we just talked about. So you can write Rust applications on the cloud. So let me show you quickly a few examples of the services that we build with Rust. First is the Firecracker VM. This is the virtual machine hypervisor that actually powers the AWS Lambda and AWS Fargate. So it's open source and it gives you really fast startup times and very low memory overhead. So you can pack much more micro VMs onto a server. So when you write your Lambda functions with Rust, actually under the hood it also runs Rust, and your application code also runs Rust. We also have BottleRocket, which is a special purpose Linux operating system that is for running containers. It's also built with Rust. It's intended to be used as the operating system for your container hypervisor nodes. So it has a lot of security features like single-step update and rollback. So you won't update part of the packages and stop with the others. It only packs the essential software to run containers. So you have much less attack services. You can use that for the Elastic Kubernetes service or Elastic Container Service. Use that nodes to run your containers on top of it. We also have the Nitro Enclave. This is for like really highly sensitive workloads. So sometimes you need to process very sensitive data like certificates, credit card information, personal health information inside your EC2 virtual machines. So Nitro Enclaves allows you to carve out a space which has additional isolation from the EC2. So you can run trusted code inside that space. And your host, EC2, can only connect to these enclaves through a socket. So you have an extra layer of security. So these services I talk about are all built on Rust, and they are licensed under open source licenses. So thank you very much. Hope you learned something interesting today. So how to build a Rust application on AWS, and also how AWS uses Rust to build the services that powers your cloud. So just a final favor, if you could fill this very, very short survey for us, it would mean a lot to us to help us improve our talks in the future. So thank you very much.
好，最后大家可以扫一下这个画面上的这个，可以做一下准备。然后我们接着要进行 Q&A 的部分，时间不太多。
Hello， 嗨，你们听得到吗 ？Hello，Hello。Okay， 好，Hi, thank you for the questions. So I see a few questions in Slido. So I'll try to answer them first, and feel free to ask more in Slido or just shout out. Not sure if I can hear it from Meet, but the first question is there any limitations on the module dependencies that we can use? So basically no. So you can add whatever dependencies you want. there's a mechanism in Lambda called Lambda layers. So you can package like shared libraries as a layer. So when you write Lambda functions on top of it, you can use these shared libraries. So this is a useful way for you to create like a base for all your Lambda functions, and you can package your dependencies there. You can actually also run Docker containers on Lambda, so that means you can package whatever you want in the Docker function. But it runs a slightly different from what I just described. Yeah, and there are a few questions on the concurrency part, right? So whether Lambda function handles multiple request concurrency. So because it's built by by the memory times time, is this still relevant to use concurrency? So concurrency in Lambda works differently from when you have your own servers. So if you have a like physical server, you will install operating system and you will write a Lambda program. You will write a Rust program that has concurrency using threads or processes, so you run a concurrency on one machine. But for Lambda, each Lambda function is one function, and then Lambda will handle the concurrency for you. So let's say you write a REST API handler that reads a request and then write to a database. If there's like 500 requests per second coming in, Lambda runtime will actually spin up 500 copies of your function and then run them. Each one is isolated from each other. And then, so there is a limit to how many you can run concurrently at one time. So for example, some regions have a limit of 1,000 per second, some have 3,000 per second. This is a soft limit, so we can increase that. So it makes your code much easier to understand because you don't have to do concurrency by your own. You write one function, and then the runtime will spin up multiple copies for the concurrency. That's how you will handle concurrency in Lambda. Of course, you can still do concurrency inside the Lambda function with your Rust code, but for most cases, you don't need to do that. There's a question about, can you run Lambda function for local debugging? Yes. So for the AWS serverless application model, there's a tool to let you try your Lambda functions locally. I do have to double check if it's fully supported in the Rust runtime, but there, like by default, there is a tool for that. Any more questions? You can also ask in Chinese, and then I can translate it for you. Okay, I guess that's the time is up. So thank you very much, and enjoy the rest of your day.
好
Thank you.
谢谢，我们谢谢旅行带来精彩的演讲。